Good morning. Thank you for coming to my talk so early. As one of my colleagues said, it's almost still night, 10 o'clock on Sunday. And I am also grateful to organizers that they invited me to this conference. I apologize for English. I live 12 years in Germany. I am from Czech Republic. I understand German perfectly, but I am unable to speak it properly. And therefore, if you would have questions, you can ask me in German, but I will answer in English. Sorry about that. I would like to be able to speak German, but somehow it does not work for me properly. In this talk, I want to answer the question why many active Postgres connections are actually not good on Linux. And this talk is marked as version 3, which means you will see updated slides, not something which is just recycled. And this talk is byproduct of my workshop about PG Bouncer and other connection poolers, and it was this talk was unexpectedly successful. I had it in China, a Postgres conference in Yinan, and also in Microsoft Online POSET conference. So it shows some important stuff, and I hope it will be also interesting and inspiring for you. I work for German company Credative, and I think you know us. We are quite old and traditional company offering support of open source products, and Postgres and Linux are our main topics. Among other topics, yesterday there were talks about Pegaprox and micro virtual machines. So we have quite a huge spectrum of experts. If you will be in urgent need of any support, call us anytime, and we will help you. Don't worry. Here are a few words about me. I worked the whole my life with any type of data processing you can imagine. So all major databases, all major data processing technologies, lately also AI, and it's all very interesting. It's sort of my adventure, diving into these things. So let's dive into Postgres. Postgres uses multiprocess architecture, and it has its historical background. This solution was chosen already in 1986 when Michael Stonebreaker launched on University California in Berkeley his PostgreSQL project, which was like second database project he created on Berkeley University. And this Postgres project was revolutionary, absolutely revolutionary in those days, because Michael Stonebreaker had experiences with all other existing databases, and he decided to make several very important architectural decisions. Extensibility is one of them, and we profit from that thing still today. But he also made the decision to use this multiprocess architecture because in those days, first of all, reliable threads were not available. Linux also did not exist yet in those days, and he also did not have enough people to implement it properly in that thread architecture, which was workable in those days. So, based on the decision, Postgres still uses multiprocess architecture, although, as I mentioned here, there is now ongoing effort to implement also threads into Postgres, and it should work in similar way as in Oracle. So we will have mixed architecture, processes, and also threads. And as I heard from Bruce Momjin on conferences, he's quite sure that in a few years this thing will be implemented, but it's still not simple to make it work, and there are also some unexpected side effects on the NUMA nodes, because NUMA nodes are now bringing another level of complexity into these things. So we will have it, but it requires a lot of work. So we still have those processes only, And they are isolated, they are stable, but they are also heavy. Here, these two pictures, they show how processes work, how threads work. It's very simplified. I think many of you have better understanding of these things than me. It just shows on a high level how different resources are being either isolated or shared. And the main point of those threads is that those threads are always running inside one process which encapsulates them. Since we have those independent processes and they do not know anything about each other because they are isolated by definition, we need some way to communicate in between them. And Linux implements this communication using shared memory, and because in Linux philosophy everything is a file, it means that this shared memory is also implemented as file system, as a special TMPFS file system. And this special file system gives us option to manipulate memory using I/O operation with files. And historically, there was just this System 5 interface into this shared memory, but it was later diminished, and we have now this libc, glibc, and mmap pass into those memories, into that memory file system. And Postgres originally, of course, used just that System 5 shared memory segment, but in 9.3 switched to these new mechanisms, to this POSIX shared memory. But internally, Postgres still creates one small System 5 memory segment because this System 5 access has a very useful option to check if other processes are running on specific directory. So Postgres uses this small System 5 segment to check if only one postmaster is accessing specific Postgres data directory, because it could happen that if there would be several postmasters running on the same data directory, then of course we will have completely destroyed data because they will not know about each other. And this System 5 segment actually makes it possible. That shared memory, that TMPFS file system, has two parts. Internal mount, which is used for shared buffers and other shared objects, and this user accessible part, this def shm directory, which from the perspective of users looks like any normal file system, but it exists in memory, and when we write into this file system, it directly allocates physical memory pages. And this def shm directory is very important for communication between processes, because those shared buffers in that internal mount, they contain data which are used across processes, but this def shm directory, it is used, for example, when main process starts parallel workers, then for these parallel workers, that main process must create files in this def shm directory to give them instruction what they actually should process. And we had one problem by one client when they migrated from Oracle, and they had like so big query that it did not fit into 1 gigabyte limitation, which is still unfortunate limitation inside Postgres. So that was a rare opportunity to see how this thing works behind the scene, because those files created for those parallel workers were so huge that they exceeded that 1 gigabyte limitation. If you work with Postgres on Docker, then you probably already encountered that there is this small default which must be increased, otherwise you will see this rare error, could not resize shared memory segment. If this error would happen on some big machine, it would be really, really bad. Here is how it looks like when we actually look at those mounts of that TMPFS file system using standard df command. So this is at the beginning just summary how Postgres handles processes and communication between them. And first thing which could be problematic is memory allocation. So Linux in these days is 64-bit architecture, and this 64-bit virtual address space, when a process touches some parts of that address space, must be mapped to physical addresses. Not the whole range of 64 bits is usually used, and that mapping is done using this hierarchy of tables, 5 or 4 levels of mapping tables depending on implementation. And as we all know, we have these standard 4 kilobyte pages and 2 types of huge pages. One is 2 megabyte big, and the other is 1 gigabyte big, these huge pages. And it is similar on other systems, just numbers could be slightly different, but the idea is still the same. And these different pages are differently mapped in this hierarchy of tables. So those standard 4 kilobyte pages, they are mapped here on this lowest level, this PTE table, page table entry. And that size 4 kilobyte was chosen back dozens of years ago when computers had completely different sizes of memory and everything. So in those days it looked good. In these days, when we have computers with terabytes of memory, it's of course a completely different story. And those other huge pages, 2 megabytes and 1 gigabyte big, they are mapped here on that page middle directory, those 2 megabytes huge pages, and here on that page upper directory, 1 gigabyte huge pages. And this thing has its consequences. And it is also important to understand how these things fit together with forking of processes, because on startup, Postgres starts that postmaster process, and that postmaster on startup allocates shared buffers and all other shared objects. But since it is a moment when all is starting, only few megabytes or few dozens of megabytes of these objects are really physically touched, and majority of those shared buffers exist only as a virtual memory in that moment. So all background processes which are forked from that postmaster in that moment inherit very small memory allocation anyway. But later, when we have multiple connections and they step-by-step touch the whole capacity of shared buffers, those shared buffers must be mapped physically. And over time, especially background writer process and checkpointer process, they will accumulate the whole physical allocation of those shared buffers. Fortunately, that forking is now quite lightweight, so when new connection is created as fork of postmaster, it inherits only a small portion of that physical mapping, and everything else is added step by step when that connection physically needs some shared buffers or those other shared objects. So forking is okay, but we still face that situation with those tables. And when I first discovered it, I thought that this is actually some mistake, that it should not be that way. But here, this blue line is actually linked to Percona article, which explains exactly this stuff. And I had also 2 months ago opportunity to see it by one client. And problem is that if we use still those standard pages on big machines, we are, heading towards big troubles, because 1 gigabytes of shared buffers or other shared objects allocated in 4 kilobyte pages requires 2 megabytes of PTE table. So if we do some theoretical maths and we would insist on connections which would be long-living for whatever reasons, then if we would have machine with 32 gigs of memory, 1/4 of it will be 8 gigabytes shared buffers, and we would try to squeeze out of it as much as possible. Let's make rather more connection than less. Then with 100 long-running connections, we can reach theoretically 1.6 gigabytes of PTE tables, and with 1000, we can reach half of that memory. I did not want to believe it until I see it in real life. Client had problems on machine, huge memory spikes. Machine had 96 gigs of memory and several thousands of connections. And fortunately, those connections have been living like 2 hours or not more. But in that moment, when we actually checked memory usage with those connections which were available, PTE tables had 6 gigabyte. 6 gigabyte across those connections. So this is actually penalty which is usually hidden and not checked. So this is the reason why mapping shared buffers and other shared objects on modern machines with huge amounts of memory, mapping them in standard 4 kilobyte pages could be actually quite disaster. And I have a workshop and talk about shared buffers where there is a recipe explaining how we can actually use those huge pages to map shared buffers using these bigger huge pages, because if we use just those 2 megabyte big huge pages, then 1 gigabyte requires only 4 kilobytes of that second level PMD table. And if we would have this theoretical situation with 1000 connection and 8 kilobytes buffers fully mapped in these 2 megabytes huge pages, it will require only 32 megabytes of PMD tables, which is really, really big difference. And this allocation of shared buffers in huge pages is now standard also on cloud environments. So if you rent a big machine, for example on Amazon, you can see that they allocate by default shared buffers in huge pages. Those huge pages can be used only for shared buffers and shared objects. They cannot be used for connections, but anyway, here you can see the difference which it makes, and also this is also the explanation why in some cases machine which uses standard 4 kilobyte pages goes into terrible memory troubles without showing anything, you know, in normal checks, because these page tables they are visible in this mem info. You can use these commands either to check total size of those memory pages or size per process. So I highly recommend to investigate this and to do that allocation of shared objects in Postgres in huge pages. Few words about NUMA architecture. This is nice and also slightly troubling architecture. In old days we had a very simple architecture, CPUs, memory, one bus in between them, which worked nicely with 1, 2, 4 CPUs, and went into terrible troubles with bigger numbers of CPUs. So machines are now internally divided into sort of independent physical machines with interconnections in between them. which means that those CPUs and memory inside that specific NUMA node have quick direct access and can benefit very strongly from this architecture. But if for whatever reason we would need to access memory on other NUMA nodes, this interconnection is slower, and here we talk about some penalty. Theoretically, that penalty means that access into memory on other NUMA node is 2 to 3 times slower, but these numbers we can measure only on a very low level. Measure them on a level of Postgres connection is actually a much bigger issue, but still depends on how we will test. And Linux offers some NUMA balancing mechanisms, which means that it can migrate processes. Of course, inside that NUMA node, that process which is running inside that NUMA node can freely jump between those cores, no problem here. But if we allow to use several NUMA nodes or the whole machine with multiple NUMA nodes, and that process will be jumping across those nodes, there is option to allow so-called NUMA balancing, that those memory pages will be migrated. And I think you immediately see what could be the issue here, because if we would have shared buffers and they will be used by multiple processes, how it is with migration. So of course, a better idea is to not allow this migrating. But there are also some mechanisms inside that balancing process itself, that those hot shared buffer pages which are touched by many independent processes are actually deprioritized from migrating. And also kernel, if it would need to migrate that page, knows also about all those physical allocations in those processes. So when kernel decides to migrate that memory page anyway, it can be finished only after kernel updates all those PTE tables. So processes which would want to access that memory page in the moment when it is migrated must wait until everything is updated. So here you can see immediately that it makes the whole situation on a NUMA node much more colorful. And therefore also using explicit huge pages can help. We will have NUMA penalty in between those nodes, but in some cases it is better than this migration. I had opportunity to test one Chinese machine, Phytium server with 64 cores, ARM64 architecture, with slightly outdated kernel, CentOS 8 lineage, and it had this very interesting architecture, 8 NUMA nodes, 4 of them with memory, those green ones, and 4 of them without memory. Everyone I showed this picture was like, what? NUMA node without memory, but it was really configured that way. So these CPUs which do not have memory banks, they must access memories on those other nodes. And in firmware of that machine, there was this table of those NUMA distances. Idea is that 10 is value inside that NUMA node, and every jump adds additional 10, meaning if there will be situation when node 0 accesses node 6, then theoretical penalty is 50. It was really done this way, but it was incredibly quick, that machine. I tested different types of mainstream load. There was this clone of Postgres, this Ivory SQL 18.3, which is very interesting Chinese clone. It has actually compatibility with Oracle. because China is now going open source. On that conference where I was, they created database, open source database association, or whatever it was named, for supporting plan of Chinese government to get complete rid of Oracle and everything, this paid stuff. And since they have like dozens of thousands or millions of applications, they do not migrate them. They created clones of Postgres which are compatible with Oracle, MS SQL, and other stuff. So this Ivory SQL has connectivity through port 1521, and when you connect to this port, you speak Oracle language with Postgres core, which is very interesting. And they have compatibility also other clones, for example, for MS SQL. So idea is that they will simply start Postgres and applications will run immediately. And I had opportunity to test it, different mainstream type of loads, and since I had only limited VPN access, I was not able to really overload that machine, but tested different types of pinning, because you can on NUMA nodes, NUMA architecture, pin either memory or CPUs or both to a specific node or group of nodes. And from what I can tell, those results were statistically insignificant. That pinning turned to be useful mainly for isolation. So if we have this machine with different NUMA nodes, we can actually use that pinning and logically divide that machine into several sort of independent parts, and can run several installations of Postgres, each isolated on some specific node or group of nodes. And since this pinning is done for postmaster and every fork inherits all those binding policies, it means that all connections will follow this binding policy of that specific postmaster. So from the perspective of that Postgres, it will be independent machine, and those databases will not actually bother each other. And as I said, those results of benchmarks which I did were, for what I could measure, statistically insignificant. It fluctuated in range of 2 to 6%, and there are much better benchmarks on the internet done by Postgres contributors, but they had physically that machine somewhere where they could test or had very good connection. So they really overloaded that whole thing and could see how performance was dropping. I could not see it, so my result was that for mainstream type of load and mainstream type of application, we may not care if it's NUMA architecture or whatever. We just need that information for pinning policies if we decide to use that machine for a multiple installation. CPU and Postgres connections. This is interesting stuff because now with new Linux distros with kernel 6.12, we get new Linux scheduler. And it changes slightly behavior of context switching, and it is changed for better. So let's explain it. Here is very simple graph showing how this context switching is being done. Process A running is interrupted, that status is stored. Process B is loaded, is processing, interrupted, so state is being stored, again process A is being loaded, and so on and so forth. That state includes CPU registers, program counters, stack pointers, transaction look-aside buffer may need to be flushed. In some modern installations, it is maybe not that necessary because newly it could be tagged with process ID. So many clever solutions, but anyway, this ping pong of interrupting and loading another process is the way how scheduler works. And we have these two types of schedulers. So until kernel 6.6, there was this completely fair scheduler, and it was, as name says, completely fair. My dear processes, here you have exactly the same portions of runtime in exactly the same intervals, so you don't need to argue, just do your job. Which is nice until we have processes which have different requirements for latency. So here this audio stream, okay. Maybe it was okay in old days. In these days, it's questionable. And this compiler, yeah, that would be definitely happy to run longer. And this is the idea of that new earliest eligible virtual deadline first scheduler. It's amazing magical name. I had to learn it, how to pronounce it. And it comes with kernel 6.6 and newer, and it was significantly improved in kernel 6.12. So new distros jump directly to this 6.12. So if you update machine from Debian 12 to Debian 13, you will get this new scheduler. And the same with the Red Hat Enterprise 9 updated to version 10. And the idea of that new scheduler is simple. Processes again get exactly the same portions of time, but differently structured over that period of run. So here that audio stream gets smaller parts more often, and that compiler gets longer part with bigger delays. It's very simplified, but you get the idea. And there is another very interesting behavior when it comes to processes which suddenly wake up. I will explain, and here is calculation. Because this is all nice, yeah, this is rocket science, what practical usage it has. So practical usage is this table, which explains this is calculation for that completely fair scheduler, which I think is still dominating on installations, because as far as I can tell, many companies are still running sort of museum of all existing Linux versions, so they will most likely run predominantly this completely fair scheduler. And here you can see a number of active tasks. Active is that important word, because if process is sleeping, it's idle, it's just waiting, and it's not part of context switching. Fun begins when those processes wake up. It will be explained on the next slide. So if there is only one process, no problem, runs continuously. With 2 up to 4 processes, up to 8 processes, that completely fair scheduler maintains a promise of a full rotation of those processes in 24 milliseconds. But also, but of course, those slices, how long that process runs on CPU goes down. So from our perspective of database administration, 2 to 4 processes actively running connections on one CPU core is the sweet spot. Because here you can see that those slices are reasonably long, that delay, that pause between them is also reasonable. Still up to 8 processes, we are sort of good, especially if we have very short transactions. Like I often see some content management system which shoots hundreds of small queries against database. So these bursts of transactions, they are usually processed in just few milliseconds. So up to 8 of these active processes is still okay. But if machine gets overloaded, here is the explanation why we see that everything is hanging and nothing is running. So if we have 64 active processes on one CPU core on 128, and I have seen such situations because, you know, everything is now dynamic. We can scale up how we want. So I have seen situation when Kubernetes scaled up microservices, and that microservice scaling created something like 800 processes on database machine with 4 CPUs because everyone wanted to immediately refresh caches, and yeah, it was a huge disaster. And of course, guess what? That was that fucking database which was guilty not being processed 700 processes in few milliseconds. Those microservices, they don't have issue. They can start that quickly. They are prepared to serve what that fucking database is doing. Yeah, this is the answer. Because with 128 processes on one core, it runs roughly 3 times per second in slices of 3 milliseconds. Yeah, well, I would like to see that microservice under this load doing some magic, you know. But of course, it's the fucking database, you know. And so this is explanation for overload. And question is, okay, why that new scheduler is better? And the difference is in situation when multiple idle processes wake up, which can happen, for example, in this case, when some services decide to get data or whatever. That completely fair scheduler, that actually had one thing which in those days when it was created looked nice, because machines had different types of loads and much less running processes. So when process was woken, it got a credit, meaning preemption right, to interrupt other processes to be processed quicker. So it had higher priority. But imagine situation now with these types of loads when dozens of processes wake up and they start to interrupt each other because they have priority. And this is exactly situation where that new scheduler works better, because it simply adds those processes as ordinary task joining a queue and does not care about any priority. It just tries to calculate their latency based on some clever calculation. So this new scheduler improves this type of jumps on machine, and we have already seen situations by one client. They wanted to upgrade Postgres. They had old Debian 9, even older Postgres. I will not say that version because it would be terrible. And they first created machine with Debian 12 and Postgres 16, and later upgraded to Postgres 18 on Debian 13. And we did benchmarking on all those machines. And surprisingly, there was significant difference in benchmarking results between Debian 12 and Postgres 16 and Debian 13 with Postgres 18. No, 1817 actually, because it does not have that asynchronous I/O, and we had seen that difference. Since everything other was relatively the same and the difference between Postgres behavior was small, we had seen this situation because that system was shooting this type of very short queries, which were processing quite often. So if you have this type of bursty loads, then just by upgrading to new version of Linux, you can most likely get interesting improvement. So to extract from it some rule of thumb, and funny thing is, I first had this rule of thumb created empirically by measurements, and only later dived into those schedulers, and actually that calculation in those schedulers proved it, because I have seen repeatedly that from 2 to 4 active connections on one core is okay, but I did not have mathematical proof, so you had seen it in that other slide. So 2 to 4 active connections, this is perfectly nice, unless of course you have very slow storage, which is unfortunately quite often case on Amazon RDS. Nothing against Amazon, I like Amazon, just their default disks have 3000 IOPS, and we very often get questions from clients, is there some sinister bug in Postgres which makes it slow? On which cloud you are? On Amazon. How big is your disk? 300 gigabytes. I guess 3000 IOPS, right? Yes, 3000 IOPS. Your SSD in laptop has 10,000 IOPS. What does it say you? You can imagine this type of problem is again blamed on database, because if you ask support of that cloud, everything is okay on their side. Of course it's okay. It's running inside nominal parameters. This is the definition of okay. If your application is slow or quick, it depends on your application. And this is the problem which we later deal with. And again, nothing against Amazon. They have their business, and I respect it. But we are then answering, these questions about really sinister behavior of Postgres. And if those developers of Postgres try to destroy their hard work on application by making Postgres really slow. Yeah, well, this is unfortunate reality. We still live in days when databases are being blamed, but it's getting better. Analytical queries, they require dedicated core, because analytical queries, they usually run quite a long time. If you have parallel workers, you must add those parallel workers. There are some other things in scaling: MVCC snapshot and relation locking mechanism, which I will mention at the end. And here comes funny question: how much memory is actually Postgres connection using? Because we all probably know the situation when we look into top command on a particular machine, and we see numbers in Postgres connections which look very strange. So if we want to get the answer, we must parse data from this smaps kernel interface. This smaps behaves sort of like normal file. Everything is file in Linux, but it's direct internal interface into kernel. So if you read data from smaps, kernel actually interrupts the process for a very short time, scrapes that memory allocation, and gives it to you as sort of text file. And it must be parsed and pivoted. And here I show situation. Well, it's quite artificial. I had empty machine. I started first ever connection, but it gives us some perspective. So this one connection, freshly started, nothing processed in it. If we go into smaps data, and we parse them based on those paths, because those memory allocations, they either have some path that they are connected to some file, or there are some special types of allocations like anonymous allocation and heap allocation. And these are those two types of memory allocation which are interesting for us. So if we look at this freshly started, completely empty connection, we can see that it was forked from that main postmaster. It has some small anonymous and heap memory. We have this size, this virtual size, RSS, resident set size, PSS, proportional set size. But if we want to be really precise, here is this private dirty, which is that memory, real private memory, which is touched physically by that process and is private to that process. But as far as I can tell, when I checked across multiple use cases, even after running hundreds of those processes, that private dirty was quite close to proportional set size. So even if you would look just at proportional set size, it's a reasonable approximation, but we will look at private dirty. And here you can see other mappings. There have been like 40 different mappings to different Linux libraries. And here you can see two special files created on dev.shm directory. That first one is actually sort of business card of Postmaster, showing everything about Postmaster, and this second is sort of business card of this process, containing data about this process. And here, this very nicely named dev0 deleted. This is that internal mount of TMPFS file system on which shared buffers and other shared objects are being created. This naming is actually for historical reasons, because of previous naming, so they kept that naming, but it's that new mechanism. So those are shared objects created by Postmaster at startup. And here you can see, because it was machined with 32 gigs of memory, shared buffers 1/4, meaning 8 gigabytes. Practically the whole size of that shared buffer is virtual memory, because resident set size, proportional set size, and private dirty for those shared buffers are very, very small. So on startup, they exist mainly as virtual memory. We can do some queries, and typically after many queries, we can see in top command something like this. Resident set size is as big, almost as big as shared buffers. So when we now dive into SMAPs again, and now we simplify it, we will not go for specific libraries, we will just summarize it based on path to those libraries. We can see immediately that all those huge numbers actually exist in that line for shared buffers, for shared objects. Dev0 deleted contains all these incredible big numbers, but if we look at private dirty, so if we summarize everything for private dirty, we of course get that horrible number. It looks like that Postgres is really badly handling memory, but it's not true, because these shared buffers are shared between all connections. So private memory of that specific connection is somewhere around 2 megabytes, because these numbers are in kilobytes. And we can do this magic later for multiple connections. This is typical situation, seeing this on machine with 32 gigs really arises happy feelings. What is my machine doing? Is it dying or whatever? And if we calculate everything from SMAPs, of course, yeah, it's almost collapsing. But if we remove that dev0 deleted, we see completely different numbers, and especially here those private dirty, they show that there could be very big differences. This one line is different, and I will explain in following slides why it is different and why it is not that big problem. So seeing this, we would need some simple tool which would go to dev0, not dev0, to SMAPs and summarize them and show us real numbers. And those real numbers are quite comfortable. We can be happy that Postgres is actually using memory quite nicely, except for this one case, which I will explain. But there is still this mystery of workmem. Everyone knows workmem setting on Postgres, and there are many nice stories about workmem, how it is being used, when it is allocated, and so on. And many of them are too nice to be true. So I made measurements. I actually scraped data from SMAP's interface repeatedly during process run, then plotted everything. And majority of those graphs are actually completely flat, except for this one, anonymous memory, heap memory, and here shared buffers. Shared buffers simply go out and stay there. But that anonymous and heap memory, they show that behavior during query run. And I have another talk about memory usage in different types of queries, and for this particular talk I just selected this very simple example because it's practically the same if you get data from some function or some table. Difference is how many data you have. So developers usually test with very small portions of data. So when they process those very small portions of data, that processing looks like this, very small burst. It's done in few milliseconds or a few hundreds of milliseconds, and that's it. So they are right when they say it works on my machine, because they see this. But if you later get more data, you see completely different behavior. But hidden in these bursts and this behavior is how much memory is being used. And I measured here that private dirty together with private clean. And private clean is very small, somewhere here. This is private clean, this is private dirty. Meaning this, orange line is private clean, blue line is private dirty, mistake, but this is anonymous memory, this is heap memory. If it's very small amount of data which fits into workmem, we would expect that machine will allocate one workmem. No, it allocates more. In my case, it allocated 1.9 workmem for that private dirty, but since it was very short burst, only a few dozens of megabytes, it was not a problem, because probability that all these bursts will happen at the same time is very low. But things gets more interesting here when data do not fit into that workmem. It requires longer processing, and Postgres puts some data on disk to process them in batches. So this is a very simple sorting. It can be spilled to disk, and it still uses this old algorithm from magnetic tapes when data have been put in batches to magnetic tapes. So internally it uses temporary tapes, how they call it. If you see in Postgres data directory those temporary files, they can be up to 1 gigabyte as every file on Postgres, but they contain many of those temporary tapes. And this algorithm is the same simply because it's the simplest, and it is still most efficient. And Postgres actually implements very interesting optimizations to not use more disk space than it really needs, and so on. So it's very nicely optimized. This is why you can see these jumps in memory allocations. But what is important here in scope of Postgres setting, I used here workmem 4 megabytes, which is standard default value on Postgres, and many clients keep it as it is, presuming that smaller amount is better. Problem is that with smaller workmem, Linux uses glibc library for memory allocations and allocates majority of that memory on heap, which it needs for processing. If that workmem would be bigger, 32 megabytes, 64 megabytes, it will use a map and majority will be allocated on anonymous memory. And that heap has that behavior, meaning it can only grow up and from top can go down. So if it goes up and stays there because there is some object on the top of that heap, even if you deallocate everything below that object, it means that that heap memory will stay allocated as it is for Linux. From Linux perspective. And this is that situation which is visible here. That heap memory stayed allocated somewhere on roughly 1.5 workmem. And this we can see later in those memory allocations in the SMAPs, that memory inside process stay high even though everything ended. Problem is with that heap memory, because Postgres can create some object on the top of that heap, and even though Postgres deallocates everything here and puts these memory blocks internally on free list, from the Linux perspective, Linux sees the whole memory as dirty memory of that process. And it was mystery for me until I found these measurements, because when I went into Postgres, into memory context tables, it showed me, no, I am using only very small amount of memory. But Linux showed me, okay, that process uses this amount of memory. So Postgres said, I don't know what are you talking about, Linux, and Linux was insisting on a huge memory, sort of big memory usage. So this is this behavior of heap, which comes with small memory allocations using glibc. So smaller workmem may not be actually as big advantage as people always think, but it depends on what is actually. Sorry, I'm taking too much time. Sorry. Yeah, very quickly, because on other conferences there is someone who says me, it's too late, 15 minutes, 10 minutes, 5 minutes, and go away. Sorry about this. So very quickly, there have been problems with snapshots overhead, MVCC snapshot scaling, and relation locking limits. There is summary. Sorry about taking so much time. The slides will be available online. I thank you very much for your patience, and I wish you a nice day.